Thanks, everybody, and thank you for all coming today. My name's Josh Michielsen. I'm a technical lead at Weaveworks.
Oh, I'm Claudia. I thought you were going to introduce me, but hi, I'm Claudia. I'm an engineer at Weaveworks.
And today, the title of our talk is Phenomenal Cosmic Powers, Itty-Bitty Living Spaces. We're going to be talking about Kubernetes on MicroVMs. We have a fantastic live technical demo with hardware that's on-site, so hopefully very exciting stuff. We're going to hop into some of the topics. We'll start off with an introduction to MicroVMs. What are they? What are they for? What is liquid metal? Liquid metal is something we've been developing over at Weaveworks, and I'll talk a bit about it. We're going to talk about why they're useful, why MicroVMs are useful, why the sort of things that we built are useful, which is all open source. You can all use it today. Free, no money down. Donations welcome. No, I'm joking. And we're going to go through a demo. So the demo is going to be about 15 minutes, so we'll be splitting the time between the talk and the demo. And so let's jump in. What is a MicroVM? It's basically a lightweight virtual machine. They're heavily reduced in terms of their device emulation support. You get no legacy support for things like legacy drivers. You get limited guest functionality, but really what they're designed for is running cloud-native workloads. They're sort of a middle ground between containers and virtual machines. You get the same level of process isolation that you would get from a regular virtual machine, but you get the sort of speed and portability of a container. So they're very quick to start up. They have a reduced attack surface because they have such a limited sort of driver and device support, and they have the process isolation of a VM. In a lot of cases, you'll get less than 100 millisecond startup times, basically. So liquid metal. Liquid metal is something that Claudia and I and a couple of others at Weaveworks have been building. It's an entirely open source sort of set of tools, and it's just basically the name for these tools that we've been building. It's comprised of Flintlock, which I'll talk about in a second, CapMVM, which is a cluster API provider, Firecracker and or Cloud Hypervisor, which are MicroVM virtual machine monitors, and Containerd. So Flintlock is a service that we've built internally. It's open source. You can visit the GitHub link at the bottom there. It is a gRPC service written in Go and provides basically things necessary in order to manage MicroVMs on physical nodes. Whether those can themselves be VMs, or they can be bare metal servers. The cluster API provider MicroVM, or CapMVM as we call it, it is a CAPI provider, also open source, and it handles the placement of those nodes, of those virtual machines across a given set of nodes, basically. Firecracker and Cloud Hypervisor are virtual machine monitors. Firecracker is an AWS open source VMM. It's the sort of thing that powers Lambda and Fargate. And Cloud Hypervisor is something that was originally developed by Intel. Both of them are built on the Rust VMM package, and both products use the KVM. I think Cloud Hypervisor even includes support for the Microsoft Hypervisor as well. They both have the same idea. They are reduced footprints, limited attack surfaces, built for the purpose of running cloud-native workloads. Containerd, we should all know what that is already. Effectively, in our stack, what we use it for is to pull and manage the images on the nodes that will be used to boot up the kernel and guest operating system within the MicroVMs. So, a bit about the architecture. Sorry. We start off with a CAPI cluster, management cluster, running CapMVM. We have some bare metal devices. Again, these can be virtual machines as well. Running Flintlock D, which is a service running on the machine. we can provide the operator can provide the YAML to CapMVM to say, I want X number of MicroVMs running on these nodes. CapMVM takes that, sends the request to Flintlock. Flintlock spins up or sends the request to Firecracker, which includes, or Cloud Hypervisor, both include a REST API, to say, spin up these MicroVMs on these nodes. And Containerd manages the images for the kernel and OS. Those MicroVMs are spun up. CapMVM handles the kubelet installation, that kind of stuff, and begins the process of creating the Kubernetes cluster. And then the operator can go and grab the kube config. So what are some of the benefits and use cases of this type of architecture, basically? MicroVMs provide, again, a level of security that containers don't provide you through process isolation, a reduced footprint, and they're incredibly fast and scalable. Both Firecracker and Cloud Hypervisor support the creation of up to 150 MicroVMs per second, with startup times in the sub 150, 125 millisecond range, and startup RAM of 5 megabytes. Some use cases: edge computing and bare metal are obvious use cases for these. CI self-hosted runners, and home labs and limited resource systems, which we'll show you today. And so we're on to the demo. I'll let Claudia go from there.
Thank you, Josh. All right. We swap places. But I need to stand here to type things.
Of course you do.
Yeah, and thank you for redoing my diagram, Josh. My diagrams weren't as pretty, so Josh has thankfully come in and done that. So yeah, this is what we're going to be showing you today, a live demonstration of what Josh was just highlighting. So this is what we're aiming for. On my Dell, this is a Dell XPS running Ubuntu 22.04. I'm going to have my kind management cluster, so that's going to be running the CAPI controllers, going to be running CapMVM, our infrastructure provider. Then here, I've got 2 Raspberry Pi Model 4Bs. These are only 4 gigs of RAM, so despite Josh saying that MicroVMs do come up fast, they do. When we're this under-resourced, it's a little bit slower, so I hope you'll bear with me on that. So on those Raspberry Pis, we have Flintlock-D, Containerd, and Firecracker, and when we're spinning up the nodes for our workload cluster, CapMVM will reach out to Flintlock-D on those boards and say, hey, give me some MicroVMs, give me some Kubernetes nodes. This is all just for fun. I wanted to bring this to the conference just because it's really cool. So I hope it works perfectly. I spent a little bit of time fiddling around with the network on this. So let me actually just talk through about the components that I've got for you. What's my next slide? I've forgotten what that looks like. Yeah. So yeah, I've got the boards. You may have noticed there's only one cable going in. I do have power over Ethernet hats because I wanted to get Ethernet and power over the same cables. I don't want to have a mess of cables going on. On my Dell, I have a local image registry, so supplying Docker images. So when kubeDM bootstraps the nodes, it cuts just literally coming from just here, not too far. I don't want to run into any rate limiting. Here, I've got a managed network switch. And the reason for this is when the MicroVMs come up, they're going to make a DHCP request. They're going to say, what's my IP, what's my DNS info, how do I connect to the outside world? And I wanted to, first of all, know what the pool was. I wanted to control that pool. And I didn't think the conference space would let me have a look at the router and see what settings were going on. Also, it gives me, I mean, I can set everything up in like my little private VLAN, so I'm doing a private cluster. And when the cluster comes up, it's going to need a load-balanced IP. Again, I need to know what that IP is. Again, I can't go and look at the conference router and find one that's just not taken and hope that it's going to stay not taken. So nice elaborate setup here. Further down, you might not be able to see this, but I've actually got this switch, don't fall off, plugged into a Wi-Fi extender. And again, this is just part of the requirements, the things that I need to do. So I needed a wired Ethernet connection to my boards. And again, I don't have a router here. So I've got my Wi-Fi extender linked up to the conference Wi-Fi, and then I can plug it into the Ethernet port. And the reason why I needed a wired connection is because when Flintlock creates MicroVMs, when Firecracker creates these MicroVMs, they are going to create a Mac VTAP interface. And I know you can do pretty much anything with Linux if you hit it hard enough, but generally you can't create MacVTAP devices with a wireless connection. So MacVTAP is just basically another type of tap device, and it's the thing that's going to get our MicroVMs access to the internet. So you see here I've got my, the guest MicroVM coming up with Ethernet 0. That is actually a MacVTAP device, which is mapped to my the VLAN interface. That VLAN interface, as a typo there, that VLAN interface is then again mapped to the Ethernet interface, which is then going out through to the switch and then chatting up to my Dell there and getting its internet access. So that is what we've got here. This is all the machinery I brought with me. So I'm just going to refer back to my notes just to see if I've missed anything. So yeah, that's all the bits and bobs. Let me now share a different screen. Actually, no, I've got one more picture. Yeah, there we go, last picture. That's all the wiring and all the stuff, so you can get a visualization in case you can't see what I'm actually working with on the desk here. So that's what we're working with, and we're eventually going to be able to end up creating a workload cluster like that, and hopefully it'll work. Again, I'm using 4 gigabyte Raspberry 4s. 8s would have been better. If you want to do this at home, in which you can, I've written really thorough docs, which we'll share at the end. If you want to do this at home, 8s would be better. They're really hard to get these days. Anyone who's tried to buy a Pi recently, it's so hard to get. I sniped some people very aggressively on eBay for these, for this demo. And 8s would be better simply because when you're creating Kubernetes nodes, you kind of want a minimum of 4 gig. Well, I'm talking memory here. I'm ignoring CPU because you get killed for memory far sooner than you'll run out of CPU, so that's fine. So yeah, when you're creating Kubernetes nodes, you really want 4 gigs of memory, especially for control planes. You can get away with 2 for workers, but if you're doing any less than that, you're really pushing it. So if you do try this at home, 8s would be better. And why would you want to do this in the first place? So if you're at home doing your home lab, maybe you're just hosting your own little app, maybe an email server, I don't know what you're doing. Yeah, you've got one board, you turn it into one Kubernetes node, great, but what if you want high availability for your apps? What if you want a second control plane node? Then that's why MicroVMs are useful, because then you can slice up the stuff that you do have without having to spend hours on eBay or with an auto-bidding system to try and get more boards to give yourself more nodes for your home lab cluster. So that's why this is fun. So I'm going to start mirroring my screen instead of, where's my display settings? Give me just a second. Mirror, do that. Let me know when it does something. Single display, do something. Oh, I have to click apply. Keep displays, yes. Yeah, sure, do that. Yay, that looks like a terminal.
It's worth noting that the vast majority of the resources required are from Kubernetes itself, not from the MicroVMs.
Oh, yeah.
You can pack a bunch of the MicroVMs onto these devices, but as soon as you start putting workloads on them, that's when you need your resources.
Absolutely. Leave room for the app. So is that all big enough for everyone? I know it's hard to see black background, stuff like that. Is that visible to everyone? All right, well, you get to see my talk notes as well, because I'm not closing those, or I'll lose my place. So, OK, what do we have here? What's in this setup? So top left, that's my local Dell. That's where the Cappy management cluster is going to be. It's actually supposed to be running automated script right now, so I don't have to embarrass myself by typing on a keyboard I don't usually use. Then on the right, we have a couple of boards. So on the top right, we've got Raspberry Pi 0. That's the one on the top. Then on the bottom, we've got Raspberry Pi 2, because by the time I got to Flash, the second one, I forgot I was 0 indexing. So let's pretend it's Raspberry Pi 1. All right, so let's crack on with that. I'm going to start the demo off, and then I'll talk a little bit more about what's running where and what's being created, because we'll have to wait a minute, because even though I am using a local image registry, there was 1 or 2 images I actually forgot to put there. So even though the images are local, they still have to go and say, do I have this? Yes, I do. Excellent, carry on. So that's going to take a second on conference Wi-Fi. So what is the first thing we're going to do? Yes. So ahead of time, I naturally created my Cappy management cluster. I did this. I set my CapMVM version. I've exported my cluster resource set because I want to immediately apply a CNI to my workload cluster. Flannel, by the way, because I just could not for love or money get Cilium working. So I've already initted that. You're not going to see that. Just take my word for it. It exists. Oh, I'm using K9s. I forgot a lot of this. So here we can see we've got CapMVM working, doing its thing. There's nothing happening right now, so I don't know why I'm showing you the logs. So yeah, that's there, ready to go. So now I'm setting up my workload cluster that's going to be running on my Raspberry Pis. So again, I'm not overloading my pies. I'm going to end up with 2 nodes per board, otherwise I'll just be pushing it. So I'm only having the 1 control plane and the 3 worker nodes. And again, that is that nice predictable private IP that's coming from my VLAN that I know where it's coming from. So I've generated that YAML. And we're going to go ahead and apply that. Actually, on the other side, let's just run a watch. So don't do that. Again, not used to this keyboard. So what we're looking at over here, there's nothing there right now, but we're just going to look at Flintlock state directories, just as a useful representation to see what is coming up where exactly. But in the documentation, there's lots more information on what Flintlock creates and where you can look for debug info later. So let's pop back over, apply that. That all looks good. There's no errors or anything. So while CapMVM is looking at that manifest and thinking, OK, what am I going to do with it? Let's actually open it up. Good idea. So yeah, this is a Cappy custom manifest. You all know what that looks like. Just going to scroll through some highlights. So here is where you say, these are my Flintlock hosts. In the future, we are going to do a more dynamic placement, so you can have like a host manager like Tinkerbell or Maz, where you can hit an API that picks up boards like that. But for now, we haven't implemented it, so I now have to say, OK, this is where my boards are. This is where you can schedule my stuff. Incidentally, while we're here, actually, if anyone has ever configured a Cappy workload cluster to use a local image registry, I've documented how to do this. There's a lot of places where you have to say, use my local registry, and that was a really fun day of trial and error to see what images were being pulled where and knowing which ones I had to load up. So yeah, you can read all about that if you want. So yeah, standard Cappy manifest. Let's see. OK, so Raspberry Pi 2, that's the one on the bottom, has picked up the control plane one. So we can go have a look to see what is running where. So I'm going to do it on the one above, just so we can not interrupt whatever that one's doing. Again, little devices, don't want to push them too hard when they're busy doing other things, and that one's doing a lot right now. So we've got system CTL status. Let's just look at some statuses. So we've got the Flintlock D service running here. So that is the thing that CapMVM is going to reach out, say, hey, create me a MicroVM. Then we also have container D. If you're going to autocomplete, no, I have to type it. Shocking. So container D, that's now pulling the images for the MicroVM, saying I need a kernel binary, I need my operating system. I can't remember what versions we're running this. I think it's 20.04 for the operating system and 5 something for the kernel. Firecracker will be running as a process, so I can actually look at that here. So we do PSAUX. Where is my pipe? Right there. Great. grep fire. So there we can see there's a Firecracker process which come up, and so that's running our MicroVM. We can also have a look at some interfaces, and here we can see this is the Mac VTAP device, and you can see that is then mapped to the VLAN interface, which is in turn mapped to the actual Ethernet NIC of the, what's it called, Raspberry Pi, that's the one. So I'm hoping that that is actually carrying on if we kick off that watch again. That one hasn't come up yet, so I hope it's actually working. Sometimes I forget, and my DHCP server gets in a weird state. So let's do a, oh, actually, I've got this part of the script. Yeah, look at that. I anticipated I would need to do that. OK, so it is working. Sometimes I forget to reboot the DHCP server whenever I switch off the Dell, and the MicroVM comes up without any network, and that's really awkward, but it's actually doing it this time. So we're actually probably now just waiting for kubeadm to boot. So we can go have a look at that. We can tail, follow, var lib flint, come on, autocomplete, var lib flintlock, all the way down to firecracker.standardout. And these are the boot logs. And it looks like it literally finished just as I opened it up. So we should now hear other things starting to pop up. So what can we do in the meantime? Let's, oh yeah, I forgot to talk about NAT. Oh yeah, so the Dell is also running a NAT forwarder, so that whenever the MicroVMs need internet, they'll get routed out through the VLAN interface. What's my, there we go. Please be correct. No. So you can use any tool to create these forwarding rules. You can use IP tables. I use firewall D for reasons, but it basically says that any traffic that comes from a MicroVM, so from anything on that VLAN subnet, just send it out through the wireless interface of my Dell, because I broke my Ethernet NIC somehow, and then any returning packets send them back the other way. So that's just how the MicroVMs have internet. Why is it not continuing? This is really awkward, because it should have been ready. Sorry? No, it should end up there, because you see, I just went a little bit further with that one than this one. So it is definitely there. Shall we look at some logs? Let's look at logs. Oh no, it's come up. Literally, it heard me. It heard me. It saw me coming. So yeah, there's the next one that's coming up. So that's neat. No, that's not Vim.
As soon as you start looking at it.
I know. It was like, I can get away with this. I'll just do nothing and she won't even notice, but I did notice. So we could have done this a while ago, but when you create a cluster with Cappy, it creates the kubeconfig and a secret. So let's go ahead and grab that. And we can then use that. Aren't you glad I'm not typing all of this out? This is a really handy tool for giving a live demo. We can then watch these nodes come up. So there's the control plane, and there's the machine, the worker node. So that's happening nicely. I thought I asked for 3. Didn't I ask for 3?
I thought you asked for 4.
Well, didn't I ask for 3 worker nodes? Oh, you hear that? So for some reason, board 0, is way louder on the CPU fan than the one beneath it. Don't know why. Actually, it might be a different OS. I think the top one's running 2204, the bottom one's running 2004. Yeah, that's much louder. And I definitely asked for 3 worker nodes. Oh, I think I'm using the wrong manifest. That's fine. Let's pretend I use the right one all along. So I'm just going to quickly, just very chill, apply. And now we're going to show how easy it is to scale to a new node. Because hopefully that should pop up another 2 for us. And let's pretend I did it right the entire time. Anyway, the nodes that are ready are there. Oh, you can see there's another one popping up. Also, it's working perfectly.
Oh no, it's putting 3 on the same one.
It's fine, Josh. Just be cool. Whatever, we have a cluster, it worked. We can now deploy stuff to it. Your blog, put some flux on it, I don't know, whatever you do with your Kubernetes. And yeah, that's it. That's the demo, how to use MicroVMs to get a little bit more out of your home lab setup.
I'm going to pop to the last slide.
Do we have a last slide? Oh, we do have another slide. Right, now I have to get there.
There we go.
Oh, that one, not that one.
We got the fun GIF. There you go.
Yeah, so this is why we chose the title. This is where I got the idea for stuff from this. I don't know why I haven't watched this since I was a child. Anyway, everything is available online if you want to scan these. This is the one on the left is the exact, really thorough documentation for the home lab setup. On the right is the liquid metal docs. Been spending months writing all of those, so I hope somebody reads them. Really thorough. So, and we finished really early, actually. So if people have questions, we have lots of time for questions.
As mentioned before, all of this stuff is open source. So nothing here, nothing we've used today is proprietary to Weaveworks. You can go play with it. All the components can be run on their own as well. So you can run Flintlock, send it a gRPC request. You don't need CapMVM. I think, does CapMVM require Flintlock at the moment?
It requires something to answer that to that API.
Yeah.
Cool. We also have like a standalone MicroVM operator if you just want to like create loads of MicroVMs with Cluster API. Or just Kubernetes, I guess. Why would you need Cluster API? Good question.
Are there any restrictions on what sorry.
No, go for it.
Yeah.
Are there any restrictions on what workloads you can run on Firecracker?
So the question was, are there restrictions of the workloads you can run on Firecracker?
What do you mean on Firecracker? Do you mean on the MicroVM process created by Firecracker?
Yeah, exactly.
Okay, so it's a MicroVM, so it depends on how you build it, because MicroVMs are just stripped down VMs. So if you haven't given it to the kernel and you haven't given it to the operating system, then no, you won't be able to do it. But there should theoretically be no limit. It's just whatever resource you set and however you build your binary, basically.
I think there was a question over here.
Yeah.
Yep.
Thanks for the demo. A couple of questions about the positioning of this. So the security benefits, you made that case. Are there any drawbacks from using this instead of just regular containers across the board, say?
Not really. I mean, I guess they're just fractionally slower. So if you really, really, really want stuff fast, And security, you've done what you can there. Maybe you're using rootless, like proper rootless, like the runc is running rootless. Then I guess maybe you'd want containers, but these MicroVMs, they're pretty fast. I can't see many drawbacks. I mean, there is a drawback. I mean, if you're running on such constrained resources, then yes, you saw it took a moment or two to start just the first MicroVM, but then we are actually waiting for kubeadm to boot, so that's out of our hands really there. But if AWS uses them in serverless, like Fargate, right? Because they are just very, very fast. You just run like your one-off thing, your one-off job, and boom, that's it.
I guess the only thing would be like if you require any of that legacy device support, then you may run into some problems. But any like para-virtualized IOs, stuff like that, and a hardware pass-through is all supported as well. So I can't think of any like major reasons that you wouldn't use them.
Yeah.
And how would you position these against, say, Kata containers with the kind of more of the hardware separation?
Yeah, so that's actually a great question. I mean, Kata containers, the cloud hypervisor supports Kata containers. So you can, I believe I haven't looked too much into it, but it's a big point on the cloud hypervisor website is that they work in tandem with Kata containers in some fashion.
I don't know enough about Kata containers to contribute to that.
That's the limit of mine.
Okay, thank you.
Any other?
We got one over here.
Have you tried wiring a firecracker up to container D inside your cluster? Going for that extra exception though?
Not yet. I haven't tried doing, I want to try doing nested MicroVMs next because you should be able to pass the KVM hypervisor all the way down through the stack and get.
Do you just want to repeat the question?
Oh, that's really good. I can't actually remember what the question now. Oh, have I tried using containerd? Yeah.
Container D firecracker.
Containerd.
Running your Kubernetes pods in the firecracker MicroVMs inside your node VM.
Yeah. Did everyone hear that time?
Have you tried using Containerd Firecracker
Yes.
to run your containers in the MicroVM?
Yep.
And we did, you answered that.
Sorry.
That was the question, though, just for the recording, for the sake of recording, and for the
Yeah, I'm bad at that. Sorry about that.
for the caption on the other side. So.
Any other questions? Actually, I'm just curious. How do you get it to when you're pasting commands into your terminal and it was like slowing it down or doing some?
Oh no, that was damn it, I should have included a link. If you just Google like auto script runner for demos in terminal, there's loads of tools out there. I can't remember what mine was. I think it's called like Demo Magic. You'd set up a file. I can actually show you if I switch to that. If I Control C here. So you just source in this script here, and then you can run commands that you just want to have run, or you can print them out, or you can print and execute them, and it will just, you run the script and it will cycle through all the stuff that you pre-programmed.
Oh, wow. That's very cool.
Yeah, it's handy so you don't have to mash the keyboard and get it wrong.
All right. Well, thank you very much.
All right, thanks very much, everybody.
Thanks, everyone.